This is the first video in a sequences of videos looking at systems of linear equations. This video is going to be the introduction video or the overview video of the high level of what's going on to look at specifics of how to solve systems of linear equations. Those will be in the following videos, and there will be a link to those in the description of this video. So when we're looking at systems of linear equations, the phrase linear equations brings up the concept of what is a linear equation. Well, we know what an equation is. It's a mathematical expression with an equal sign where two sides of that equal sign have to be the same thing. By linear, what we mean is all variables are raised to the first power. Now, coefficients of linear equations can be any number we want. So for instance, 4x minus 7y equals 23 is a linear equation. Y equals 3x plus 4 is also a linear equation. 4 times x minus 3 plus 8 equals 1/5 times y minus 6.7. It's also linear equations. If you look at each of these terms has a single variable raised to the first power. Again, if you don't see an exponent, it's assumed to be 1. Now, there's a little bit more to it than that. For instance, we also don't allow x being multiplied times y, and we also don't allow x to a first power in the denominator. But for the sake of an intro video, you should think variables need to be to the first power. Coefficients and constant numbers can be anything we want. Now, to transition from a linear equation to a system of linear equation, a system of linear equations is simply multiple linear equations. So it's as simple as that. When we have a bunch of linear equations together, that is a system of linear equations. In fact, anytime we have multiple equations together, it is a system of equations. So for example, I could have taken two linear equations, the first two I had on my previous slide, and those two linear equations together as a unit constitute a system of linear equations. Now, as far as linear equations go, and specifically a system of linear equations go, the goal of a system of linear equations usually is to find a solution. So we want to find a solution to a system of linear equations. A solution is going to be an ordered pair or a point which satisfies all the equations in the system. Now, before I move on, what we have seen in the last few slides, we've had two variables in all of our equations. Once you get into multiple variables, then a solution is going to be an ordered triple if we have 3 variables, or an ordered quadruple if you have 4 variables. So in other words, the more variables, the more points, the more entries in a point. But for the most part, we're going to look at systems of linear equations in 2 variables, and then we'll expand that to 3 at the very end. So a solution to a system of linear equations is a point which satisfies all the equations in the system. Now, in our example of 4x minus 7y equals 23, and y equals 3x plus 4, it turns out that negative 3 comma 5 is a solution to that system. So how could we show that that's a solution? Well, negative 3 comma negative 5 is a point. We could plug that point into both, equations. So take my first equation, 4x minus 7y equals 23, and hopefully we've done a lot of, or hopefully you have seen a lot of equations and ordered pairs. If not, you can check out one of my videos on that. But with ordered pairs, we always put the x term first and the y term second. So we plug in the negative 3 into the x. We replace y and plug in that negative 5 in for the y. Once you simplify the left-hand side, 4 times negative 3 minus 7 times negative 5, you get 23 on the left-hand side, and also you get 23 on the right-hand side. So that's a true statement, and that means that the point, negative 3, negative 5 works in that first equation. So it works in that equation, meaning it's a solution to that equation. Now, working in one equation is not enough to be a solution to the system. So we'd also want to check the other equation. So let's take that other equation. And again, plug in negative 3 in for the x value and negative 5 in for the y value. When I do it in the second equation, you'll notice that on the left-hand side, we get negative 5. On the right-hand side, we also get negative 5. So the point, negative 3 comma negative 5, works as a solution in the equation y equals 3x plus 4. Since that point works as a solution for the first equation and also works as a solution for the second equation, that means negative 3, 5, negative 3, negative 5, is a solution to the system. Okay. So it has to work as a solution in both equations in order to be a solution to the system. Now, what is not a solution? Let's check out some other points. Let's check out the point 1, 5 in that same system and the point 4, negative 1 in that same system. So we go back to our system. Let me start a new page. and then plug in 1, 5. I'll do 1, 5 first. So we'll plug in the 0.15 to both. Oof. I don't know why that keeps coming that way. All right, so I take 4x minus 7y equals 23. I replace the x with a 1. I replace the y with a 5. That becomes 4 minus 7 times 5. I get negative 31 on the left. And 23 on the right. So 1, 5 is not a solution to this first equation. Now, honestly, I can stop there. But I'm not going to. So again, this is not a solution to 4x minus 7y equals 23. So technically right now, I know that it's not a solution to the system. But I'm still going to go ahead and plug it into the other equation as well. So the y equals 3x plus 4. If I plugged in 1, 5 to that, I'd end up, whoops, let me go through this, end up replacing the y with 5, the x with a 1, and my equation becomes 5 is equal to 7. So 1, 5 doesn't work there either. Excuse me. So it doesn't work for this other equation, which is to say it's not a solution. Okay, so since I get false statements on both, that means 1, 5 is not a solution to this system. Okay, now like I said, we actually only need it to fail in one of these two. So let me just write that down, what I just said. 1, 5 is not a solution to the system. Okay. There we go. Like I said, we only actually need it to fail in one. So for instance, let's test the point that was given to me on the slide, which was 4, negative 1. I plug it in to my first equation, 4x minus 7y equals 23. I replace the x with the number 4, replace the y with the number negative 1, simplify, and I get 23 equals 23. And that starts out well. So let me write that. So for -1, works for, or is a solution for, that first equation there. When I say works for, that's just another phrasing to say is a solution for. So it's a solution to the first equation. However, if we look at the second equation and I plug in -1 for my y and 4 for my x, what happens is I end up getting an equation that says -1 is equal to 16, which is obviously not true. Therefore, the point for -1 does not work for y equals 3x plus 4. So what does that mean for the system? Well, in short, if it works for one but doesn't work for the other, it does not work for the system. Therefore, the point for -1 is not a solution to the system. So that's how it goes. To be a solution to the system, it has to be something like -3, -5, where we plug it into the first equation and it gives me a true statement. So it's a solution to the first equation. And we plug it into the second equation and it gives me a true statement. If both of those things happen for all of the equations up there, then the point is a solution to the system. If the point doesn't work in either equation, then that point is not a solution to the system. And if the point works in one but doesn't work in the other, then also it is not a solution to the system. So that's the idea of what a solution to the system of linear equations looks like. Our goal is going to be able to find that solution. It turns out in our system, there was actually only one point that worked. That is -3, -5. So not only is this a solution, but this is the only solution to this system. And there's no other ordered pair that works in both equations. Now, the reason that there was only one solution is because if you think about these linear equations graphically, all of the solutions to each one of these linear equations can be graphed as a straight line on a Cartesian coordinate plane. So 4x minus 7y equals 23, that's actually graphed in the red line here. All the solutions to that system are points on the red line. Y equals 3x plus 4, that is well, I should say all of the solutions to y equals 3x plus 4 are graphed on the blue line. Notice that most of the time when we have two lines, they're going to cross at a single point. And therefore, you can see this graphically. The point there is -3, -5. That's the point at which the two lines cross. And so that's the only point that's going to work in both equations. Now that is the most common option for solutions. If you're given two linear equations in two variables, most of the time we get one solution. And that's when we have two lines interacting at a single point, at a single ordered pair. However, there are other options for what could happen. If you think about having two lines, there is a scenario in which we have two lines that are parallel. Hopefully we know that parallel lines never cross, and therefore parallel lines are going to have no solution to the system of linear equations. And then it's also possible if we were given two equations with two variables, that those two equations are actually the same line. And if that is the case, then there are infinitely many solutions to our system of linear equations. Now, these are the options for two equations when we have two variables. So when we have two variables and two equations, these are the three options we get. The most common is that the two lines cross at a single point, but you could end up with a no solution case in which we have parallel lines, or the infinitely many solutions cases where we have one line that's really the same line as the other. If you go into more variables and more equations, it's a little bit more complex than just looking at lines on a two-dimensional graph. But still, if you have more variables and more equations, we still could end up with just one solution, or we could end up with no solution, or we could end up with infinitely many solutions. Again, it's not graphically the same thing, because if you have more variables, then you have to graph in more dimensions. But we get the same types of solutions, either one, no solutions, or infinitely many solutions. And so now that we know what a solution to a system of linear equations is, the goal is going to be to find the solution that we want. Find that solution to the system of linear equations. And in the next few videos, we'll look at a few ways to do that. We'll look at a few techniques of how to find those solutions. The first is by graphing. Another technique that we'll use is the elimination or the addition method. And then a third technique that we'll use is substitution. So that's what we'll do to find solutions or a solution to a system of linear equations.